Hi everyone, welcome to GoClasses. How are you all? Good evening. Good evening, Arnav, Mavit, Swegtandu. So let's start now. Before we start, please tell me audio, video volume, is everything clear? Let me know. Okay, so let's start now. Now in this session, what we are going to do? We are going to do the complete revision of pipeline. Okay. Uh, each and every gate previous year question we will take. Okay, each and every gate previous year question, every gate question we are going to cover in these lectures. Okay, in this revision lecture. So let's quickly start pipeline complete revision. Okay, so to in this lecture, what I want to do, basically, first we will see pipeline introduction, then we will see some gate questions. Okay, most of the gate questions come from this topic, pipeline introduction. Okay, pipeline performance. Let me tell you, like in the gate exam, almost 50% questions are coming from pipeline performance only. Okay, so the basic questions are coming in the gate exam from the pipeline, most or almost you can say 50% questions. Okay, then we will see data dependency and hazards. What is data dependency? What is data hazard? What is the difference? This difference is very important. Okay, because in the gate exam there are two questions on this difference, and many good questions can be created on this difference. What is the difference between data dependency and data hazard? What is the difference? Okay, so that difference we will see. So this is the I can say content for this lecture. Now let's start without consuming any more time. So let's just start. And also tomorrow you have all India mock test too, right? Okay, so tomorrow you should attempt, like once this session is over, then just go to sleep and wake up tomorrow morning and attempt all India mock test 2. Okay, now let's start. So pipeline. Let me tell you, you already know pipeline. Let me tell you, like this is the most natural concept in computer organization. This pipeline is a very natural concept, not only in pipeline, not only in computer architecture. Forget about computer architecture. In your real life, this pipeline you will see everywhere. Okay, so you already know and understand pipelining. Let me tell you, of course we will start now. We will see the revision, we will see gate questions, everything we will see. But let me tell you that you already at this point of time, you already know. Okay, you already understand pipeline. All you have to do, just apply your concepts, just apply your common sense. Okay, that common sense you have to apply on the gate questions, and all the gate questions will be done. So let me tell you that from the pipeline, all the gate questions, actually forget about gate questions, all the questions, most of the questions, they are common sense based question. Let me tell you. Okay, from this pipeline, most of the questions are common sense based. Like you can easily solve those questions with your, I can say, common sense. Okay, that we will see. Don't worry. I will take all the gate questions, so you will see that. Now, anyway, so you already know and understand pipelining. Now let me prove it to you. For example, pipelining is everywhere. Okay, like pipelining in the construction. So have you seen this type of scenario whenever there is some construction at some construction site, maybe at your house, at your home? Okay, so this type of scenario you might have seen. Okay, so this is called pipeline actually. This is called pipeline. So you can see this is called pipeline. Now let me tell you what is happening here. Okay, let's analyze this construction pipeline. Let's analyze this. Okay, so for example, let me assume that here you have all the uh, have you seen the Swades movie? There is a Swades movie by Shah Rukh Khan. Okay, so in that movie there is a scene there that here they are constructing some okay, at this point they are constructing some wall, some sorry, some wall or something they are constructing. And okay, so here they are constructing some, I can say, water tank they are constructing. Sorry, okay, so I can say water tank. So some water tank they are constructing. This construction they are doing, and so from here they have to take the bricks. So let's assume here you have all the bricks are here. Okay, so all the bricks, and this is like this is a I can say this is some mountain or something. So you can see here you have all the bricks. Okay, Now you tell me, this is two scenario I am giving you. What I am giving you, I am giving you two scenario. One scenario is a non-pipeline scenario. Okay, the first scenario that I will give you, that is non-pipeline scenario. PL means I will, when I say it means pipeline. Okay, so non-pipeline scenario, let me give you. So what happens? What you can do? Let me assume that you want 20 bricks here. Let me assume you need 20 bricks. Okay, you need 20 bricks here, and let me assume that here these are the steps, like one step, 2, 3, 4, 5, 6, and like 7. Okay, so let's assume these are the steps. So now you tell me, if there is one person in the non-pipeline, in this non-pipeline scenario, so let's assume there is single person here. Okay, he's taking one brick, and then he's putting that brick here, then coming back. Sorry, and don't worry about the coming back. So basically, first one person will take one brick, go here, another person will come take one brick, go here, then another person will take one brick, go here, one after other. Like once this is done, then the next person will go, then the next person will go. So now you tell me how much time it will take. Like how much time it will take to basically take all these bricks, all these 20 bricks at this point. So tell me, what is the time, how much time we will need? Tell me. So how much time we are going to need? So you can notice that the first person, 1, 2, 3, 4, 5, 6, 7. So 7 steps it will take. Okay, once these 7 steps are over, then the next person will go. Okay, then the second person will go, then the third person will go. Okay, yes or no? So tell me how much time it will take. So it will take 7 multiplied by 20. Yes or no? Because we need 20 bricks here. So 20 people will go. Like first, the first person will go. This person number 1, when it will go here, this person number 1, when it will go here. Okay, when it is done, then after that, the next person will go, right? Then after that, the next person will go. Yes or no? Okay, so once this is over, like once this is over, then this person will start, then this person is going to start. Okay, then this person will go. So can I say that this much amount of time it will take? Yes or no? Like whatever. So this much amount of time it will take, 7 into 20, right? Yes or no? Correct. Okay, 7, then 7, then 7, then 7, and so on, 7 into 20. So this much amount of time it will take. Now what is the better thing to do? Tell me. Like for example, all these people, they don't know what is computer architecture, but they know pipeline, they understand pipeline. They don't understand computer organization, but they understand pipeline. So tell me what they will do. They will create a pipeline. They will create pipeline means, okay, what will happen? So these are the 7 steps. So now what will happen? One person will stand here. So basically you are dividing your hardware. Like you can consider these people as hardware. You are dividing your hardware. Okay, so this hardware you are dividing. Okay, this hardware you are dividing like this. This hardware you are dividing like this. Okay, so now you tell me. Now you tell me how much time it will take. Again 20 bricks. Again, to bring 20 bricks, how much time now it will take? Now what will happen? Now this is going to happen. So okay, so the first brick, look at the first brick, look at the first brick, look at the first brick. That will go here, then 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 that will go here. Okay, then here, and then here. So tell me, did we save any time for the first brick? Did we save any time for the first brick? For this first brick, is there any time saving? There is no time saving, right? Yes or no? There is no time saving. Okay, so for the first brick there is no time saving. Definitely there is no time saving. For the first brick, what will happen? You will need total 7 steps for the first brick. This will happen for the first brick. Okay, now you tell me about the remaining. Now you tell me something beautiful will happen. Something beautiful is going to happen. What is going to happen? See what is going to happen. When the first brick is here, when the first brick is here, then the second brick is here, right? Yes or no? Correct. When the first brick is here, when the first brick is here, then the second brick is here, and the third brick is here, right? Yes or no? So now you tell me, like when the first brick is here, finally, when the first brick is here, then the second brick is here, right? Okay, so now you tell me how much time it will take for the remaining bricks. For the remaining 19 bricks, they are coming one after other, right? Yes or no? So total how much time you are taking? Only 26 units. Yes or no? So a lot of time you are saving or not? A lot of time you can save or not by this pipeline execution? Yes or no? Did you understand this? A very simple, I can say, a very simple scenario that we observe in our real life. So this is the construction pipeline. Yes or no? So basically your hardware, this is you can consider this as your hardware, and this is your, like, your hardware you have divided. This is like your hardware you have divided. Okay, your hardware you have divided. Is this clear? So the hardware, so total 7 people, the hardware you have divided, but here you did not divide the hardware. Okay, here you have a single hardware, so that hardware you did not divide, but here what you have done, you have divided the hardware, and finally I can say 26 units it will take. This much amount of time it will take for 20 bricks. Okay, for 20 bricks this much amount of time it will take. And in this scenario you can see for 20 bricks this much amount of time you need. So tell me which is beneficial, pipeline or non-pipeline? Tell me which is beneficial, like which you will prefer. Definitely you will prefer pipeline, yes or no? Did you understand this? Please tell me. Pipeline is very natural concept. It is very, very, very natural concept. You can notice that this pipeline happens all around you in your real life. You will always see the pipeline happening. Okay, this pipeline, this concept is applied in all the fields of, I can say, of our real life. So did you understand this problem? Did you understand that when the first brick is here, then the second brick will be here, then the third brick will be here, then the fourth brick will be here? Okay, so did you understand this, that we will need only 26 units of time? Only this much amount of time we will need for 20 bricks. So we can take 20 bricks from here to here. We can take 20 bricks in 26 amount of time. And in the non-pipeline scenario, we need 140 units of time. So definitely this is your pipeline. Okay, so now let's see another scenario. Like, another scenario is your oil pipeline. In the oil pipeline, what happens? Like, this is your oil pipeline, right? Correct. So for example, again the same thing will happen. Like, let's assume that here you have some tanker. Okay, now here you are discovering some suddenly you discovered oil here. Okay, so here you suddenly discovered oil. Okay, now what do you need? So let me assume that you want to fill this tank. Again, there is this tank. You want to fill this tank, and you have a bucket. So this is you, and you have a bucket. And let's assume this bucket can put, like, I can say, like, this bucket has the capacity of 25%. Okay, so this bucket can take almost, I can say, 1/4 water. So 1/4 oil of tank. 1/4 of tank, I can say. Let's assume this is the size of this bucket. Now you tell me, and let's assume that you are taking 3 days. Like, if you want to go 1 day, 2 day, 3 day. So for example, now here what will happen? Tell me here what will happen. If you apply non-pipeline scenario, then what is going to happen? In the non-pipeline scenario, you are not dividing your hardware. Is this clear? Is this clear that you are not dividing your hardware? Okay, like, you have a single hardware. This single hardware you have. Okay, what this single hardware will do, please understand, this is very, very, very important. You have this single hardware. Okay, you have this single hardware. You are not dividing your hardware. Now what this, because this is a single hardware, so what it will do, first it will do one work, then it will do the second work, then it will do the third work. Do you agree? Yes or no? Because you have a single hardware, so it will do one work at a time. It will do one work at a time. It will do one work means one instruction. Okay, so it will do one instruction at a time. It can only do one instruction at a time. So you can see that you have a single hardware. Now what the single hardware will do, it will take 1 day, 2 day, 3 day. In 3 day this will be filled. Okay, so this will take how much time? This will take 3 days, right? Yes or no? This will take 3 days. Then again what will happen? Then again this will happen. Then again this will happen. So it will take 3 days. So tell me, how much amount of time you will need to fill this tank? How much amount of time to fill this tank? How much amount of time you will need? So can I say that you will need total 12 days, right? Yes or no? Okay, so total 12 days you need. Correct? Very simple. Now you tell me, if you have pipeline, like, what you do something smart. Okay, you do something smart, like, you can make a pipeline here. So this type of pipeline you can you can make. Okay, so this type of pipeline, let's assume this type of pipeline you can make. Now you can make this type of pipeline. Now what will happen? See, this first bucket, look at this first bucket. This first bucket, what you will do, this first bucket you will put here. Now this first bucket is going. Okay, this first bucket is going. Now you tell me, how much time for single bucket? How much time for single bucket? This single bucket, how much time it is taking? This single bucket, how much time it is taking? The first bucket, how much time it is taking? This first bucket. Again, it will take the same 3 days, right? Yes or no? It will take again the same 3 days. Okay, because there is no, I can say, we do not have any benefit. The first bucket has to travel. Okay, the first bucket has to travel, so it will take 3 days. The first bucket will be here, no problem. Okay, so there is no benefit. There is no benefit. But now what will happen? Something beautiful will happen. As soon as this first bucket will be here, okay, you can very easily, within small amount of time, you can get second bucket, then you can get third bucket, then you can get fourth bucket. Yes or no? Like, this is the benefit. See, the first bucket will take same amount of time. Like, the first bucket will not give you any advantage. The first bucket will not give you any savings. But what will happen after that? All the buckets that you have, after that, second bucket, third bucket, fourth bucket, they will not take 3 days. Okay, they will take maybe 1 hour, maybe 1 hour. Maybe this will take 1 hour, maybe this will take 1 hour, maybe this will take 1 hour. So did you notice a lot of savings you have? So if you do this pipeline, with this pipeline, a lot of savings you can do. So finally, it's like, I can say 3 days plus 3 hours. Okay, so a lot of savings you can do, right? Yes or no? Is this clear to everyone? Please tell me. Something like this, like, this is just analogy. Don't go into the exact data. Like, don't worry, sir, why 1 hour, 2 hour? Okay, so don't worry about the exact data. This is just analogy. Did you understand the concept of pipeline, in the pipeline and non-pipeline? Okay, so this is a very natural concept. Let me tell you, like, for example, what is the concept of pipeline? The concept of pipeline is that never waste time. Okay, never waste time. This is the concept of pipeline. Pipeline means never waste time. Do not waste time. This is the concept of pipeline. And let me tell you, this pipelining concept, this is a very natural concept. This is very, I can say, you will see this concept everywhere. In every field, you will see, in every field of real life, you will see this pipelining concept. So basically what we are doing in the pipelining, what we are doing, multiple instructions, they are, I can say, they are executing parallelly. Like, you can notice here, multiple instructions, they are executing parallelly. Like, for example, you can see, when the first brick is here, then the second brick is here, then the third brick is here, fourth brick is here. So you can notice simultaneously, okay, simultaneously, many bricks, multiple bricks are going towards here. Yes or no? Simultaneously, multiple bricks, multiple instructions are executing simultaneously. Multiple bricks are executing simultaneously. Okay, so this is the concept of pipeline. This is a very simple concept. Okay, is this clear to everyone? Tell me. Now let's see this question. Tell me the answer. Quickly tell me the answer. So many of the slides I have taken from Georgia Tech University. So there is a pipeline course by Georgia Tech University. So many of the slides I have taken from Georgia Tech University. Like, this question is taken from, let me tell you the source of this question. This is Georgia Tech University. Okay, anyway, so tell me the answer for this. Quickly tell me. So there is a laundry pipeline. What is laundry pipeline? There is a washer. One load of laundry, it will do in 1 hour. Okay, let's assume one load of laundry, it will do in 1 hour. Then you have dryer. Okay, one load of laundry, it will do in 1 hour. And then there is a folder. Okay, again, one load of laundry, it can fold in 1 hour. Okay, so they are taking 1 hour, 1 hour, 1 hour. Now, okay, if you do not have any pipeline, then what is going to be your, how much time you will need? If you have no pipeline, if there is no pipeline, then how much time you will need? So for 10 loads of laundry, so for 10 loads, you will need total 3, 4. This is for one, right? Okay, this is for one load of laundry. I can say this is for one load of laundry. Okay, so now you tell me, with the pipeline, how much time it will need? With the pipeline, how much time you will need? With the pipeline, how much time you are going to need? See, very simple concept, that the first load will take 3 hours, right? Yes or no? The first load will take 3 hours. Agree? the first load will take 3 hours. But when the first load is here, when the first load is here, okay, then the second load is here, then the second load is here, and then the third load is here. So you can notice that the first load will take 3 hours. This is for first load. This is for first load. Okay. But the remaining 9 loads, they will take only 1 hour. Okay. The remaining 9 load of laundry, they will take only 1 hour. So finally, how much time? Okay. Only 12 hours. Yes or no? So what is the speed up? What is the speed up? What is the speed up of, like, what is the speed up this pipeline will provide you over non-pipeline? What is the speed up of pipeline over non-pipeline? How much speed up it is providing you? How much speed up did it provide you? Okay, how much speed up did it provide you? Like how much faster it is, how much faster this pipeline is. Okay, so you can clearly see that this non-pipeline was taking 30 hours. This non-pipeline divided by pipeline. Okay, so this non-pipeline was taking 30 hours and this pipeline is taking only 12 hours. So finally, how much speed up did it provide? This much. Okay, this is your answer. So this much speed up did it provided you for 10 loads of, for 10 loads of laundry. Is this clear? Tell me. So this is a simple question. This is a simple quiz. What is happening here? Did you understand? Did you understand what is happening here? Because you can notice that the first load will take 3 amount of time. Okay. The first load will go here, then it will go here, then it will go here. But what will happen when the first load is over? Then the second load will only take 1 hour. Then the third load will take only 1 hour. Fourth load will take only 1 hour, and so on. So finally, I can say that the first load will take 3 hours. The remaining 9 load will take only 1 hour, only 1 hour. So the finally you will need only 12 hours. Okay. But in the non-pipelining, you will need 30 hours. Now you tell me a simple question again, I am asking. Actually, let me tell you this, when you do this non-pipeline, in this actually the hardware is not divided. Okay. This hardware, you can consider this as a single, like, okay, see, let me tell you, this is something important actually. That is the reason I'm telling you. So when you have this non-pipeline, okay, when you have this non-pipeline, what actually it means? It actually means that you have, it's like you have a single machine. It's like you have a single machine. Okay. So this is non-pipeline laundry. This is non-pipeline laundry machine. Or okay. So in the non-pipeline laundry machine, actually there is a single machine. Remember, please remember. So there is a single hardware. You can understand that there is a single hardware. Okay. There is a single hardware. Of course, in this single hardware, you have, in this single machine, you have the facility of washer. You have the facility of dryer. Okay. You have the facility of folder. Are you getting my point? Okay, have you seen this type of like washing machine? Think about the washing machine that you have in your house. In your house, you have a washing machine. Think about that. Tell me, do you have 3 washing machine? Do you have three machine? Do you have in your house? Do you have 3 machine? Do you have a different machine for washer, different machine for a dryer, different machine for folder? Do you have that? You don't have that. So because we cannot afford it, right? Yes or no? So that will be very expensive, and that is not needed in our house. In our house, what we will do? Maximum 1 or 2 laundry we will do in one day. Okay. So in your house, you have a single hardware. Please understand, this is something important. Okay. Because many students, they don't understand this clearly. Okay. They don't understand the difference of pipeline and non-pipeline clearly. This I have seen, and there is one gate question in which if you don't understand this difference, then also you can solve that question. Okay, that question you can still solve, but you will not be satisfied. Okay, so if you don't understand this difference, so please understand this difference. What is happening here? Like non-pipeline laundry, okay, it's like your house. In your house, you have a single machine. It's like a single machine. Okay, single washing machine. So remember, this is like a single machine. In the single machine, you have the facility of washer, dryer, folder, these facility you have. So this machine is taking, I can say this machine is taking 3 hours. Okay, this machine is taking 3 hours for one load of laundry. Okay, is this clear? So this is the data. Actually. Okay, so when this is given to you, when this is given to you, this is given to you, and I ask you, what happens when you have no pipeline? Okay, then what you have to consider? Tell me what you have to consider. Like this photo is given to you, and I tell you that there is no pipeline. I tell you there is no pipeline. Then what you will consider? Then you will consider that this is a single machine. This is a single hardware. Is this clear? Is this clear to everyone? Tell me. So this photo I give to you, and then I tell you that there is no pipeline. There is no pipeline. It simply means that we did not divide our hardware. We do not have like we did not like separate our hardware. It's like a single, I can say single hardware, or you can say single atomic unit. You can say it's a single atomic unit. Okay, you have to consider this as a single atomic unit. You have to consider. Okay, so this is what I'm saying. Now you can notice that. So this is like, the analogy is very simple. In your house you have a single machine. This single machine has the facility to do washing, drying, folding, let's assume. Okay, so basically this is your non-pipeline laundry machine, which is taking 3 hours for a single load. Now what this pipelined laundry machine is, what this pipelined laundry machine is, pipelined laundry machine, what is that? Can anyone give me what is the analogy for pipelined laundry machine? It is like a shop. It is like a I don't know, in India I have never seen this. In India I have never seen that this type of shop where people go out and they have laundry. But in this there is a series Friends. Okay, so there is this series Friends. In this Friends I have seen this type of system. I have seen in this series. Okay, so there is a TV series Friends. Okay, anyway, so what happens in a pipeline laundry machine? You can consider like a shop. You can consider like a shop. So this is, in this shop what happens, like you can consider this is a machine. This is a machine which only does the washer. This is a machine which only does the washing. This is a machine which only does the I can say whatever, like drying. Okay, and this is the machine which does the folding. Okay, so you can consider like this. Is this clear? Okay, so you can consider like this. Now you have divided your hardware. Now it's like your hardware 1, hardware 2, hardware 3. Okay, so now you are separated. Basically now what you have done, you have separated your hardware. You have separated. Now what is happening? Now this is happening that this is taking 1 hour, this is taking 1 hour, and this is taking 1 hour. Okay, is this clear? Tell me, is this clear? So you can consider this pipeline laundry as basically you have divided your hardware, this pipeline laundry. Okay, in this pipeline laundry, what you have done, you have separated your hardware like this. Okay, in the non-pipeline laundry, what you are doing, there was a single machine. Okay, did you understand the difference between pipeline and non-pipeline? In the pipeline, what we do, basically, it's not like for example, let me give you an example. In your house you have a washing machine. Can you use it as a pipeline? Like in your house, think about your house. In your house you have this washing machine. Can you use it as a pipeline? Like, can you do this, that okay, when something is drying then something else is washing? Can you use it? No. What you will have to do, tell me. In your house you have this machine, this washing machine you have. Can you use it as a pipelined machine? You cannot use it, right? You cannot use it because it is a single atom, a single entity. It is a single hardware, single entity, single machine. You cannot do that. So tell me what you will have to do. What you will have to do, tell me. Okay, if you want to convert this machine, if you want to have a pipelined laundry machine, then what you will have to do, then you will have to divide these facilities into 3 hardwares. Do you agree? These facilities, these 3 work, you have to divide into 3 hardware. Okay, these facilities, these facilities, okay, these facilities you have to divide into 3 hardware. Okay, 3 hardware. So this is what I'm telling you. So the difference in pipelined and non-pipelined machine, did you understand? What is pipelined machine? What is non-pipelined machine? So in the pipelining, basically, we have separate hardware. Okay. Like basically we divide the hardware. You have your hardware, that hardware you are dividing so that you can use so that you can have a pipelined, I can say pipelined system. Is this clear? You have your system. In that system, what you do, you separate the hardware. Okay, you separate the hardware, then you will get a pipelined system. Then you can use that system as a, I can say, to execute the multiple instructions at the same time. Please tell me, is this so far, is everything clear? This point is not, I can say this point is very important actually. That is the reason I'm telling you this point. The difference of pipeline and non-pipeline, this difference is really, really important. Okay, so far everything is clear. Like in your mind, just have this analogy. Okay, this analogy, right? Your washing machine in your house, washing machine in your house, that is the pipeline, that is the non-pipeline. Okay, in your house, the washing machine that you have, that is non-pipeline. Okay, and in this shop, the washing machine that you have, that is a pipeline. So for the pipeline, what you are doing, you are separating the hardware. Okay, so that you can execute multiple instructions at the same time, so that you can execute, like when drying is happening, when someone is drying, then someone is else is washing, someone else is folding. Okay, so you can do multiple things at the same time. Okay, so that is the reason we divide hardware. Okay, now let's move on. So this is the point. So what is pipeline? Pipeline will improve your efficiency by executing multiple instructions at the same time. Okay, so you can see pipeline is an implementation technique in which multiple instructions can be executed at the same time. Okay, now let's move on. Now what we are going to do? Now pipeline in a processor. So far we have seen the analogy, right? Did I give you any processor so far? We did not see any processor, right? We have only seen the analogy so far. And remember, analogy is not a concept. Okay, analogy is just for understanding, that is not a concept. So now what we are going to do, we are going to see how we can use pipeline in a processor. Okay, now there are two concepts actually. First, let me tell you a concept of single, I will tell you that. Okay, don't worry. I will tell you pipeline and non-pipeline in a processor. Now let's see. So what happens? You already know, whenever a instruction is executing, it will, what it will do, you will fetch the instruction. Okay, right, these things you will do. So basically when an instruction is executing, like this instruction, where this instruction is executing, this instruction execution is happening, then what you will do, then first you will instruction fetch, first you will fetch the instruction from the main memory, sorry, from the instruction memory. Like this is your instruction memory. From the instruction memory you will fetch the instruction. Then what you will do, after fetching the instruction, what you will do, you will decode this instruction and you will read the registers. Okay, you will read the registers. Then what you will do, okay, you will decode. You want to find out which type of instruction this is this addition instruction, subtraction instruction, multiplication instruction, load instruction, what type of instruction this is. Okay, and you want to read the register. Okay, for example, if your instruction, let me assume that your instruction is add r1, like this is your instruction, add r1, r2, r3, and let me assume this is the destination. Let me assume this is the destination. Okay, so it means you are adding and you are putting into r1. Okay, so you can see that what you will do, first you will fetch this instruction I1 you will fetch. Okay, here you will fetch the instruction from the instruction memory. This is your instruction memory. From the instruction memory you will fetch the instruction to the in your CPU. Okay, now after that what you will do, you will do the instruction decoding. You want to find out which type of instruction this is this addition, load, store, multiplication, what type of instruction this is. You will also read the registers. You will read the register, the source register. You will read r2, r3. Okay, you will read r2, r3. So the source register you will read. Then what you will do, after that you will do the ALU, right? Yes or no? Okay, you will do the ALU. So these registers that you are reading, these registers you will add. Okay, you will add them. This addition, actually the actual addition will happen. Okay, so what will happen here, r2 plus r3 will happen. Here I1. Okay, so now after that what will happen, after that, if there is any need, see, for this instruction there is no need. For this instruction we do not have any need, but if there is any need, then okay, anyway, let me make it simple, let me keep it simple. So if there is any need, then you can access the data memory also. If you have any need, then what you can do, you can access data memory. Okay, access data memory. Like, let me give you a scenario where you have this need. Like, let me give you this scenario, so you can access data memory. Why you want to access the data memory? In this we do not need this, right? Yes or no? Do you agree? For this addition instruction, there is no need to access the data memory. The data memory we don't need to access for this addition instruction. But maybe for some other instruction, okay, like for example load instruction. Like, consider this load word. This instruction you consider like R1, and consider this load word instruction. Like, consider this type of instruction. In this, what this means, this means load word. What this instruction means, this instruction simply means that in R1 you put, what you put in R1, what you put memory 2 plus R2. Okay, in the memory, this is like you are accessing the memory. This is your data memory. Okay, this is your data memory. You are accessing the data memory. Okay, and this is the address, and this is the address, and this is the address, or I can say address of operand or data. Okay, address of data. So you can see now in this load instruction what will happen again. Tell me in this load instruction again what will happen. You will fetch this instruction. So this I2 will come from the instruction memory. There is an instruction memory. Okay, from the instruction memory this I2 will come in the CPU. Okay, then what will happen, then you will decode this. Okay, you want to find out whether this is load instruction, store instruction, addition, multiplication, what type of instruction this is. So you will decode this, you will read the registers. Okay, you will read the registers. Like, what are the registers? You will read the source register, this R2 you will read. Okay, so here you will read the register like R2, this register R2 you will read because this is the source register. Okay, so you can see this is the source. So you will read this, and this is the destination. This is the destination. Okay, now what will happen after that? After that you will use ALU. Tell me one simple thing I'm asking, a very simple thing I'm asking. This load instruction, what it will use ALU for? What it will use ALU for? For this address calculation, right? R2 plus 2, right? Yes or no? So this load instruction, what it will do? This address calculation. So finally, this will use ALU for address calculation. Now you have this address. Okay, now this is your address. Now what you will do? Tell me, now what you will do? You have this address. Now what you will do? You have this address. Now what you will do? This address you have. Then you will access the data memory. Yes or no? Correct, right? So now you will access the data memory. This data memory you will access. Okay, so from the data memory you will access, you will get this data. This data you will get, and finally that data where you will put, you will put in the register, right back in register, right back in register, right register. Okay, so whatever data you got, whatever data you got, you will put that in R1. Okay, you will put that in R1. Okay, so very simple. So this is your point. Access data memory means M of R2 plus 2. Okay, so this is the complete explanation. Like, I am saying that I am just telling you a simple scenario. I am telling you, okay, a simple scenario. I am telling you that, see, this is okay. So you can see that, for example, if you have this instruction, add R1, R2, R3, then what you will do? You will fetch this instruction, decode this instruction. You want to find out, decode means you want to find out which type of instruction this is. Is this addition, multiplication, load, store? Then you will read the register, you will read the source register R2, R3, you will read, then you will execute the ALU. Okay, then you will use the ALU to compute R2 plus R3. Then there is no need for this, right? Yes or no? For this instruction, for this I1, for this addition instruction, there is no need. There is no need for this. But anyway, this will happen because all the instructions, they will go, they have to go through the same path. Yes or no? See, this addition instruction does not need to access data memory, right? Yes or no? Do you agree? This addition instruction, it does not need to access data memory, but still this phase will happen. Okay, but still this phase will happen. In this phase, this addition instruction will not do anything. In this phase, this add instruction will not do anything. but still this phase will happen. Like in this phase, this addition instruction will be, I can say, will be idle. Okay. So after this, what you will do? After this, write register. After this, write register. So here what you will do basically, in this, you will write this value. This value you will write into R1. Okay. So this is the point. This is your instruction execution. I've told you about the instruction execution. Very simple. Now you can notice. Now you can notice what happens in this instruction execution. What happens? So let's see this instruction execution. Look at this instruction execution. Look at this instruction execution from hardware point of view. Look at this instruction execution hardware. Okay. Look at this instruction execution hardware. Now I am creating the hardware. Okay. The diagram of hardware I will create for this instruction execution. So what is happening here? Just give me a second. Okay. So now let's see from the hardware point of view, like how the instruction execution will happen. Let me create the hardware, how the things will happen in the hardware. So you know there is a program counter, right? Okay. What this program counter will do? There is a program counter, correct? This program counter will tell you where is the next instruction. Okay. This program counter, this is going to tell you where is the next instruction. So from this program counter, okay, you will take the value. You will take the value. Where you will go? Tell me where you will go. Where you will go? You will go to the instruction memory. Okay. You will go to the instruction memory. From the instruction memory, what you will do? You will go to the instruction memory. Okay. So basically from this program counter, you will take the program counter value. Okay. You will go to the instruction memory. That instruction you will take. For example, this instruction you will take. Now, after this, what is the next stage? After this, once this instruction, okay, you are fetching this instruction. Now this instruction has come. After this, what will happen? After this, decode will happen. Okay. This decode will happen. This decode will also happen. Also, what will happen? The second thing, what will happen? This decode will happen and register read will happen. Okay. You will read the register. This is your register file. This is your register file. Okay. So you will read the register. So two things will happen. You can notice. First, you will fetch the instruction. So it's like, this is like instruction fetch. You are fetching the instruction. Okay. Then what will happen? Then you will decode the instruction. You want to find out which type of instruction this is. Is this addition instruction, multiplication, load, store? What instruction is this? Okay. Then what you will do? Okay. At the same time, you will read the source register. You will read now, like for example, focus on this add, focus on this instruction like addition R1, R2, R3. Okay, so what will happen? You will read the source register. This source register you will read. After that, what will happen? Tell me. After that, this execution will happen, right? Okay, so after this, you will go to the ALU. Okay, so this ALU execution is going to happen. Okay, so many people they create diagram like this. So this is your ALU. So the ALU execution will happen. So you will compute R2 plus R3. This R2 plus R3 you will compute. After that, tell me for this add instruction, just tell me a simple thing. For this add instruction, what will happen then? What is the next step for this add instruction? What is the next step for this add instruction? For this add instruction, the next step, yeah, memory is not needed. Okay, so what will happen? You will add this R1 plus R2 plus R3. You will do this. You will do this, and where you will put? You will put in the register file, right? Yes or no? You will put in R1. You will put in R1 write back. This is called write back. So now, did you understand why this is called write back? Did you understand why this is called write back? Did you understand why this is called write back? Like why this word write back, back, B-A-C-K. Did you know this? Did you know this? Why this is called write back? Did you know this? What is the reason we are putting this back here? B-A-C-K. Okay. So anyway, so you can see that this is called write back because what you will do, okay, whatever, like this R2 plus R3, and this you will put in the register file, you will put in the R1. But remember, if your instruction is load word, if your instruction is like this R1 and then something like 2R2, okay. So if your instruction is like this, then what will happen? Tell me. Then what will happen? If your instruction is like this, load word. Now in this situation, what this ALU is doing, that is the address, right? Correct. Okay. So you can see that in this situation, if your instruction is load word, then what this ALU is doing, that is the address of the data memory. Okay. So from here, you will go to the data memory. So from here, you will actually go to the data memory. there you will read, okay, there you will read this data you will read, and that data again you will write here. This is the hardware I am telling you. Okay, this is the, so because the data that you will read, remember, very simple point, the data that you will read, you will put in the R1. Okay, so that is the what I'm saying, the data that you are reading you are putting in the R1. So this is the hardware, this is called data path. Did you understand this? Please tell me, this instruction execution hardware, or I can say this data path, did you understand this? Let me know. Very simple, right? Yes or no? Okay, so this is a simple instruction execution hardware. Now let me tell you what happens. There is one thing is called pipeline. Now remember, if you have no pipeline, then what it means? Tell me. I already told you in the laundry example, if you have no pipeline, then what it will mean? If you have no pipeline, then what it will mean? Then you will consider this as a atomic hardware. Yes or no? Correct? If you think of this as no pipeline, if you think of this as no, see, if this is no pipeline, if you have no pipeline, then it simply means that, it means that this hardware, this is one atomic, I can say this is one, I can say single atomic entity, right? Yes or no? I can say, like, you can consider this as single atomic hardware. Okay, is this clear? If you have no pipeline, if there is no pipeline, then basically, okay, then there are no stages, like you don't have any stages. For example, if there is if there is no pipeline, if you do not have any pipeline, then it's like all these things, this is like a single atomic hardware. And let me assume this is taking, for example, maybe 20 nanosecond. Okay, maybe 20 nanosecond this is taking for one instruction. Remember, this is one complete thing, this is one complete thing, one atomic thing. So let me assume that this is taking 20 nanosecond per instruction. Per instruction it is taking 20 nanosecond. Okay, one instruction, for one instruction it is taking 20 nanosecond. Now actually what is happening here, so let me tell you, like, basically this is called single cycle execution. Okay, is this clear? This is called single cycle execution. This non-pipeline execution, this non-pipeline execution that you have, this non-pipeline execution that you have, that is called single cycle execution. What it means? This non-pipeline execution that you have, that is called, that is basically single cycle execution. What this single cycle execution means, that it's like this 20 nanosecond, okay, one instruction will execute. Okay, in these 20 nanosecond, like one cycle time is 20 nanosecond, you can consider this as one cycle time is a 20 nanosecond. In these 120 nanosecond, only one instruction can execute. All these things will happen in one cycle. Is this clear? Is this clear? What will happen? Like, all these things will happen in one cycle. Okay, so your one cycle time is 20 nanosecond. In one cycle, all these things will happen. In one cycle, your instruction will execute and the time is 20 nanosecond. Okay, because the instruction will execute in one cycle. This is called single cycle execution. Okay, now in the pipeline, now you can notice that, so you have 20 nanosecond. Here, you tell me, if you have, for example, 100 instruction, then how much time it will take? Tell me, if you have 100 instruction, then how much time it will take? For 100 instruction, how much time you are going to take? You are going to take 100 into 20 nanosecond. That is like 2000 nanosecond. Okay. Now what we are going to see, now we are going to see what happens when you have pipeline. Now I want pipeline. So when you have pipeline, then what you will do? You will divide your hardware. This hardware that you have, this hardware, now this hardware is basically divided. Okay, you have separated your hardware. Of course, you have to do some extra work. Okay, some extra work you will have to do. You need to separate this hardware. So what you are going to do, this is what you are going to do. Okay, so what you will do, you will separate your hardware. Like, you will consider that this is your some hardware unit, which is instruction, which will do instruction fetch. This hardware stays hardware 1, or I can say, maybe you can call it stage 1. You can call it stage 1. So this stage 1 is responsible for instruction fetch. It will do the instruction fetch. Okay, it will do the instruction fetching. Then this stage 2, it will do the instruction decoding. This is your stage 2. Then this is your stage 3. Then this is your stage 4. And then finally this is your stage 5. This right back, this is your stage 5. Okay, so you can see that basically, if you want to take the benefit of pipeline, if you want to execute many instructions simultaneously at the same time, okay, concurrently, if you want to execute many instructions, then what you will do, you have to do some changes, right? Yes or no? So what you will do, this hardware that you had, this, okay, this previous hardware that you have, like this hardware that you have, what you will do, you will do some changes, and you will divide it into, I can say, you will separate the hardwares, so that now this stage will do the instruction fetch, this stage will do the instruction decode, this will do the ALU, this will do data memory access, and this will do write back to the register. So this is what is happening here. So finally now you have the pipeline. And of course what will happen now, what will happen, for example, maybe this stage is taking, oh, every stage, let's assume every stage is taking, let's assume 4 nanosecond. So that total is 20 nanosecond, because total was 20 nanosecond, right? Yes or no? Okay, total was 20 nanosecond. Total, all the work, all the work was happening in 20 nanosecond. Now what you are doing, now you have divided this this stage. So you have divided the task, the complete task, the complete instruction execution task, you have divided into 5 stages. Okay, the complete execution task, you have divided this execution task, you have divided into 5 stages. Okay, now let's assume every stage is taking 4 nanosecond. Let me assume every stage is taking 4 nanosecond. Every stage that is taking 4 nanosecond. Now you tell me, for 400 instruction, how much time you will need? Now you tell me, for 100 instruction, if you have 100 instruction, then on the pipelined processor, now you, okay, on the pipelined processor, how much time you will need? On the pipelined processor, how much time are you going to need for 100 instruction? For the first instruction you need, see, the first instruction will, what the first instruction will do, first instruction will go here, then go here, then go here, then go here, then go here. So the first instruction will do 20 nanosecond, right? This will happen for the first instruction. This is going to happen for the first instruction. But after that, the remaining 99 instruction, the remaining 99 instruction, they will only take 4 nanosecond, right? Yes or no? The remaining 99 instruction, the remaining 99 instruction, they are going to take only 4 nanosecond, because in every cycle, okay, one instruction will now execute. So finally, how much this data, whatever, what is this data, tell me. So you can calculate this. So this is 416. So 416 nanosecond. So you can see here you have 416 nanosecond, and here you have 2000 nanosecond. So tell me, which is useful? Which is useful? So definitely pipelined execution is useful. Okay, so this is the complete system. You can see this diagram, you can see this is the pipelining the processor, pipelining in the processor. Okay, so very simple, you can check it out. Okay, so when you are pipeline, then basically what you are doing, let me tell you, like when you are pipeline, then what will happen? Like here, when you are pipeline, then what will happen actually? The pipeline, then this will happen. So you have like in cycle 1, then cycle 2, then cycle 3, then cycle 4. Every cycle is taking 4 nanosecond, 4 nanosecond, cycle 5, cycle 6, and so on. So what will happen in the cycle 1? I1 will go to instruction fetch. So for example, let me put it here. This is instruction fetch stage, this is instruction decode, this is execution stage, this is your read your data memory, you are reading the data memory, and then write back. So now you can notice, in the first cycle, instruction I1 will go to instruction I1, you will fetch instruction I1. In the second cycle, what will happen? This instruction I1 will go to the decode state, right? Okay, you will decode the instruction I1, you will read the source register. Okay, you will read the source register, you will read, then you will execute, then this instruction I1 you will execute, then it will go, then you will read the data memory, and then you will finally you will do the write back, and that's it. This is okay. Then this will go, then this will go away. So this instruction execution is over. Now you can notice that very simple in the pipeline execution, what will happen? Because you have separated the hardware, right? Yes or no? You have separated the hardware. Now because of that separation, what will happen? That's that separation of hardware that you have done. So because of that, what will happen in the cycle 2? In the cycle 2, when this I1 is doing, when this I1 is in the ID stage, okay, this instruction I1 is in the decode stage. This instruction I1 is in this stage. Okay, this instruction I1 is in this hardware, in this phase. Okay, or is working on basically this hardware is working on I1, I can say. Okay, so when this instruction I1 is here, then what you can do, this hardware can work on instruction I2. Okay, when this hardware is working on I1, then this hardware can work on I2. So this is what can happen. You can notice that in the next cycle, in the second cycle, when the instruction I1 is in the ID stage, then you can fetch I2. This I2 you can fetch, okay, in the instruction. So this I2 instruction you can fetch. Then when this I1 is in the execution stage, when this is in the execution stage, then this I2 can go to the decode stage. Okay, then what will happen? This is in the, this is I can say it is reading the data memory, it is accessing the data memory. At that time, what this I2 can do, this I2 can go to the execution stage, and so on. Okay, so and so on. Now similarly, you can notice in the cycle C3, what can happen? In the cycle C3, I3 can go to the instruction fetch. You can fetch the instruction I3. In the cycle C4, instruction I3 can go to the decode stage, and so on. Okay, so this is what is happening in the pipeline. In the pipeline, this beautiful scenario is happening. So in the pipeline, what will happen? For the first instruction, you will take 20 nanosecond, but after that, but after that, see, for the first instruction, you will take 20 nanosecond, but after that, what will happen? After that, in every stage, one instruction will, in every cycle, one instruction will come out. Okay, when this will come, in the next cycle it will come, in the next cycle it will come, in the next cycle it will come, and so on. So you can notice that uh, so for the first instruction you will need 20 nanosecond, but after that the remaining instructions, all the remaining instructions, they will need only one cycle. Okay, and this is your cycle time. One cycle is taking 4 nanosecond. So in every cycle, one instruction will come out every cycle. So the remaining instructions will take only this much amount of time. So that is the reason total time is 416 nanosecond. Okay, so this is the complete scenario. You can check it out. This is what is happening, okay, in every cycle. So you can notice in this diagram, if you did not understand, in this diagram you can notice that this I1, how much time this I1 took? Tell me, how much time this I1 took? This took 20 nanosecond. Okay, this took 20 nanosecond. This I1 took 20 nanosecond. This I1 started here and it went here. But now, when this I1 is done, when this I1 is over, how much time this I2 will take? Once this I1 is done, when this I1 is over, this I1 is over, then how much time this I2 will take? Then I2 only have to take only one cycle, like right? Because for I2 only this stage will be remaining. For this I2, for this instruction I2 only this stage will be remaining. So after one cycle, after 4 nanosecond, I2 will be done. After 4 nanosecond, I3 will be done. After 4 nanosecond, I4 will be done. So after every cycle, one instruction will be done. Okay, so very simple, very simple. Okay, so this is the point. Now let's move on. So let's take this question. Tell me the answer for this one. Tell me the answer for this question. Now, Swagtendu is saying that, sir, suppose one instruction is not using some of the stages, then also execution cycle time will be added. Yes, Swagtendu, there are many different type of pipelines. Okay. So the pipeline that we have in our syllabus, these are simple pipelines in which all the instruction go through all the stages. Okay, this line you will see in many questions, but this is not like, if they don't give you, then also it is like, I can say it is just understood, because the in all the books also, in like for example, for the computer organization, you have Patterson, you have Hamacher. In all these books also, they cover the basic pipeline only. Okay, so the pipeline that we have in our syllabus, in those pipeline, all the instructions, each instruction will go through all the stages. Is this clear, Swagtendu? All the instructions will go through all the stages. And let me tell you, there is another pipeline. There is something called super scalar system. Okay, but those things we don't have in the syllabus. There is something called super scalar system. Okay, so there are some complicated, of course, what we are learning right now, this is the basic idea of pipeline. This is the most basic fundamental idea of pipeline. But remember, in the practical, in the real life, of course, complicated things are done. Okay, also there is a concept of super scalar system. I will not discuss that, but this concept is there. Okay, in that concept, in the same in the same stage, at the same time, you can have many instructions. Okay, so there is a concept of super scalar system. Okay, so don't worry about those things. Basically, the in our syllabus we have the fundamental, or I can say basic pipeline we have in our syllabus. Okay, and we assume that uh, all the instructions, they go through all the stages. Okay, every instruction will go through all the stages, whether you do, whether you don't use that stage or not. Okay, in that stage, whether you do nothing or not, okay, whether you do some work or you don't do some work, that is irrelevant. Every instruction will go through all the stages. Okay, now let's see this one. So tell me the answer for this question. You have 5 stage pipeline. There is a 5 stage pipeline in which you have total 5 stages of the hardware. So you have separated your hardware into 5 stages, one clock cycle per stage. Every stage is taking one clock cycle. Okay, in every stage you are spending one clock cycle, you are spending in every stage. There are 10 instructions in our program. If you don't have any pipeline, then tell me. If there is no pipeline, remember, if there is no pipeline, it simply means there are no stages, right? Yes or no? Array, yes or no? If you don't have any pipeline, you do not have any pipeline, then there are no stages. You don't have any stages. You can consider no pipeline means you can consider this as an atomic hardware. In this hardware, all the things are happening, all the things, all these 5 stages, things are happening here. Okay. So basically, you don't have the concept of stages when you have no pipeline. If you do not have any pipeline, then you have to consider the entire hardware as a one atomic entity. Your entire hardware is basically single atomic entity. So when you do not have any pipeline, then there is no concept of stages. We do not have any concept of stages, like stage. We do not have any concept of stages. Okay, so very simple. When you have no pipeline, then in this situation you will notice that for 10 instruction, each instruction will take how much time? You can notice 5 cycles. Okay, because one stage is one cycle. But remember, in the non pipeline, when you do not have any pipeline, there is no stages, there is no concept of stages. Please understand, there is no concept of stages. You do not have any concept of stages. But it does not mean, that you don't need to do these things. Okay, right? Yes or no? Do you remember my example that I told you, this laundry example? Laundry in your house, laundry in a shop. Okay, so in your house also, you do not have concept of stages, you do not have concept of separate machine. But your machine can do all those 3 things. Yes or no? Your single machine can do washing, drying, and that folding, right? Yes or no? So this is what I'm saying. So when you don't have any pipeline, no pipeline means there is no concept of stages. But it does not mean that, you don't have to do the work. Of course you will do this work. Okay, so these 5 cycles will be taken for one instruction will take 5 cycles. So total 50 cycles you will need. And if you have pipeline, then what will happen? If you have pipeline, then the first instruction will go through all the stages. First instruction will go through all the stages. The first instruction, this is for first instruction. So the first instruction will go through all the stages. It will take 5 nanosecond, because one clock, it will take 5 clock cycles. 5 clock cycles it will take. But the remaining instructions, they will only take one clock cycle. Okay, the remaining instructions, all the remaining instruction, the remaining will take only one clock cycle. So finally you have 14 clock cycles. Okay, is this clear? What is the speed up for 10 instruction execution? for 10 instruction execution. For when you are what is the savings? Like, forget about speed up. What are the savings? How much time you are saving for 10 instruction execution? When you are executing 10 instruction, then how much you are saving? That will be 50 minus 14, right? Yes or no? Okay, so like if I ask you savings for 10 instruction execution, that will be 50 minus 14. These many clock cycles you are saving. Okay, anyway, so let's move on now. Now let's see. So many examples you can create. You can create, for example, you can create a two-stage pipeline. Okay. uh, okay, so you can create a two-stage, so these things you can read. I leave it up to you, you can read. So basically you can also have two-stage pipeline like this. Okay, now one concept I want to tell you, that concept is basically inter-stage buffer. There is a concept of inter-stage buffer. Let me tell you that concept. Okay, so this inter-stage buffer, inter-stage buffer, what is this concept? Inter-stage buffer. So it simply means that, first of all, you tell me a simple question I'm asking. This concept of stage, in which you have pipeline or non-pipeline, this concept of stages, this concept of stages you have only in pipeline, right? Yes or no? This concept you only have in pipeline, because what we do in the pipeline, we separate the hardware, right? Like, this is the instruction fetch hardware, this is the instruction decode hardware, this is the execution hardware. Okay, like this. So it's like, basically, this is like stage 1, stage 2, stage 3, stage 4, like so and so on. So like, this is your hardware, you can say. This is your instruction fetch hardware, this is your hardware, instruction decode hardware, and so on. Now you can notice that in the pipeline you have this concept of stages. You can call this hardware, this hardware, this hardware. These are the stages of the pipeline. Okay, you are separating the hardware. Now, whatever hardware you have, this hardware you are separating like this. Okay, you are separating like this. Now in the pipeline, what happens? Because in this pipeline, you can notice many instructions are executing at the same time, right? Yes or no? Like, many instructions, they are executing concurrently. When some instruction is here, then the next instruction is here, right? Okay, so when instruction I1 is here, then I2 is here, then I3 is here. So many instructions are executing simultaneously at the same time. Okay, so what we need, basically, when we do this hardware division, when we separate the hardware, these hardwares we are separating into stages. Okay, then some information, basically, if you want to propagate some information from S1 to S2, this stage, if it needs some information from S1, okay, this stage, it wants some information from S1, then tell me, is it useful that that it will I can say, mm, you tell me, like, for example, S2 wants some information from S1. Now whenever this S2 wants some information from S1, is it good that it will use this S1 for itself? Is it good that this S1 will be used for that information, so that the next instruction will not execute on S1, right? Are you getting my point? See, a simple point. Are you getting what I'm saying? I'm saying that when this S2 needs some information, this is your hardware, this is your instruction decode hardware. Okay, in this stage you decode and you read the register. Now in this stage, if you need some information from S1, let's assume I want some information from S1, then S1 is already executing some instruction, right? Okay, this is executing I1, this is instruction, this is executing I1, this is executing I2, but I want some information. This S2 needs some information from I1, from S1. Then definitely it is not good that, like, you are using this S1. Okay, so what you can do, the best thing is, you can use some registers, like some registers you can use here, and in these registers you can put all the information that is needed by S2 from S1. Okay, are you getting my point? So in these registers, this register, the inter-stage register you can use. In these registers, what you can do, you can put the information, this information you can put. Okay, this information you can put, whatever information you want from S1, that information is available here, so that this S2 can use that information. Similarly, If this S3 needs some information from S2, then it can need from here. Also remember, maybe this S3 needs some information from S1, right? Yes or no? Maybe this S3 this S3 needs some information from S1, then also it can use it. Then also it can use this buffer. So basically, what you use this entry stage buffer. This is basically used to store information. Used to store information. Okay, this information will be used by later stages. Okay, this so used to store information used by later stages. Used by later stages. Okay, so this is the concept of entry stage buffer. So this is the final point, that basically in your pipeline, okay, this entry stage buffer concept, this concept is only in the pipeline. When you do the pipeline, when you separate the hardware, in that situation, now you have these stages. This is your stage one, then there is a entry stage buffer, then this is stage two, and this is another register. See, these are registers, like these are basically simple buffers, or you can call them registers. These are simple entry stage registers. They hold the information. They are used to hold the information which is required by the later stages. The later stages, they will use this information. Okay, the later stages, they are going to use this information, and so on. Okay, and so on. So you can see this is the concept. Now okay, and one more thing, that all these things, like whether the stages or these registers, all these registers, all these stages, they are basically synchronized by a clock. Okay, all these things, they are synchronized by a clock. They are synchronized by a clock. Okay, so and anyway, so more I will discuss about this more, like what is this clock, what is the cycle time. I will discuss all these things, but anyway, you can see that all the stages and all these inter stage registers, inter stage buffers, they are basically synchronized by a clock. So there is a clock which is synchronizing all these components. Okay, so this is the concept of inter stage buffers. So very simple concept, you can notice, but this concept you only have in the pipeline. Remember, in the non-pipeline, there is no need, right? Yes or no? Why? Can anyone tell me? In the non-pipeline, if you do not have pipeline, then we do not need these buffers, because there is no concept of stages. Very good. Okay, because in the non-pipeline, you do not have any concept of stages. You don't have stages. Okay, because you don't have stages, so there is no need of inter-stage registers, inter-stage buffers. So you can easily see. Okay, let's move on now. So your pipeline can be anything. Your pipeline can be 4 stage, 5 stage, 8 stage, 10 stage, 100 stage, 2 stage. Your pipeline can have any number of stages. For example, this is a 4 stage pipeline. Look at this. Look at this pipeline. This is a 4 stage pipeline. There is instruction fetch, instruction decode, and read the register. Okay, so in this hardware unit, this is the hardware which will do the instruction fetch. This is the hardware which will do the decoding, and it will read the registers. This is the hardware which is responsible for execution, like ALU. Okay, and then you will write the results in the registers. So you can see this is a 4 stage pipeline, and these are the inter stage buffers. Okay, all these are the inter stage buffers. Okay, depending on the pipeline, the last stage also can have the inter stage buffer. Is this clear? Like, that depends on the pipeline, of course. Okay, that depends on the pipeline. Depending on the pipeline, depending on the requirement, the last stage also can have inter stage this buffer register, but mostly it is not needed, but some pipelines will need. So depends on your pipeline, depends on your requirement. So depending on the pipeline, the last stage, it can also have the inter-stage buffers. Okay, but anyway, this is the simple point. So remember, your pipeline can be 4 stage, 5 stage, 100 stage, 10 stage, any stages you can have. It depends on you, how many how many basically stages you want to create. But tell me one thing, when you are creating the stages, like for example, if I am creating 10 stages, it simply means that I am dividing my hardware into 10 components, right? Yes or no? Okay, my hardware that I have, that hardware I'm dividing, I'm separating that hardware into 10 components, so that these components can execute in parallel without disturbing each other. Okay, So if I have 10 stages, it means I'm dividing my hardware into 10 components. These components should work independently. Okay, it should not happen that one component is disturbing another component. If one component is working, then another component cannot work. Okay, that should not happen. This is called structure hazard, that we will discuss in the next lecture, don't worry. Okay, so anyway, what I'm simply saying that one component should not disturb another component. All these components that you have, 10 components that you have, in the 10 stages, every stage is a hardware. Okay, every stage is a hardware component. Every stage will do some work. Okay, so all these components, they should not disturb one another. Okay, they should be completely independent. Okay, anyway, so let's move on now. Now let's see performance analysis of pipeline. This performance analysis we will do in the ideal world. First, we will do in the ideal world. Like, tell me, what is the most ideal world? In the ideal world, what will happen? We will do the, remember one thing, before we see this performance analysis, let me tell you, most of your gate questions are coming from this performance analysis. I can say almost 50% gate questions are from this. Is this clear? Almost 50% gate questions, gate PYQs. And this is the most easy topic actually. This is very easy topic, and almost 50% gate PYQs are from this. So anyway, what this performance analysis is, let's see in an ideal world. In an ideal world, what will happen? See, this will happen. In an ideal world, you are thinking, let's take this laundry example. Let's consider this laundry example. This is your house. This is your house washing machine. In the house washing machine, you have washer. You know that, okay, all the components are in the same machine, right? In the same machine. So this is a single machine. You can notice this is a single hardware, single machine. In the same machine, you have the facility of washer, you have the facility of dryer, you have the facility of folding. Okay, and you already know, for example, you already know that, okay, when I do the laundry, then it is taking 1 hour. Okay, it is taking 1 hour, it is taking 1 hour, it is taking 1 hour. Now tell me, if I convert this non-pipeline to pipeline, then what is the most, I can say, what is the most ideal situation? Tell me, this is your non-pipeline, right? Correct. This is the non-pipeline. Now, when I convert this non-pipeline to pipeline, now I am converting this to pipeline. I am converting this to pipeline. Then what is the most ideal situation? Okay, what is the most ideal situation? The ideal situation will be like this, that, right? The ideal situation will be like this, that this washer still needs only 1 hour, right? Yes or no? This will be the ideal situation, correct? Are yes or no? The ideal situation will be that this washer needs only 1 hour. Like, the time should not increase. Okay, the time should not increase. The dryer should, okay, the dryer needs only 1 hour. The this folding also takes only 1 hour. Like, the time should not increase. For example, it should not happen that time is increasing. Okay, so here washer is taking 1 hour, and suddenly now washer is taking 2 hour. In ideal world, this should not happen, but in the real world, this can happen. The time can increase. Okay, so this is just an analogy. Okay, but try to understand what I'm saying. I am saying that this washer, this is the ideal world. Okay, and in the ideal world, you can also assume that these inter-stage registers, these inter-stage buffers, they also have zero delay. Okay, they also have zero, I can say, zero delay. They also have no delay. So you can assume that they also have no delay. They also have no delay. So this is the ideal situation. Now, in the ideal situation, what will be the non-pipeline and what will be pipeline in the ideal world? So you tell me a simple question. So what I'm saying, is this understood? So in the ideal, like completely ideal world you are living in, let's assume, in the ideal world, let me assume that I'm giving you some data. Let me assume that non-pipeline, you have a non-pipeline processor, non-pipeline CPU. So this non-pipeline CPU, what is it doing? Let's assume it is taking some amount of time. For example, maybe it is taking some t amount of time. Okay, a non-pipeline. So let me assume this is tn. N means non-pipeline. Okay, so let's assume this is taking tn. This is taking tn amount of time. Okay, so what is this tn amount of time per instruction? This is taking per instruction. So this much amount of time it is taking per instruction. For one instruction, it is taking this much amount of time. Now, in the pipeline CPU, when you convert this into pipeline CPU, let me assume that you are making k stages. You are making k stages. Okay. And what is the ideal situation? Tell me. Tell me. What is the ideal situation? The ideal situation is that per stage will take Tn divided by k. Yes or no? That is the ideal situation. Correct or not? Do you agree or not? Like pipeline CPU, okay, there are k stages, and let me assume that one stage is taking Tn divided by k. This much amount of time per stage. This much amount of time. I can say this much amount of time per stage. One stage is taking this much amount of time. Okay. So very simple. So here, one more thing I want to tell you. Very simple. Do you remember I told you when you have known pipeline, that is basically single cycle execution? Yes or no? Do you remember I told you non-pipeline CPU simply means single cycle execution. That is called single cycle execution. So this Tn is basically cycle time of non-pipeline CPU. Okay. This is the cycle time, right? It's 20 nanosecond. You can assume this is like 20 nanosecond per instruction. 20 nanosecond per instruction. So this is the cycle time of, I can say, non-pipeline CPU. Non-pipeline CPU. This is the cycle time. Now you have 5 stages. Let's assume you have 5 stages. Then it simply means in the pipeline, okay, this is the cycle time. In the pipeline, this is the cycle time. In the pipeline CPU, this is the cycle time of pipeline CPU. Okay, this is the cycle time. So this is the ideally. Now you tell me one by one. I'm asking you few things. You tell me all the things. So what is going to be one instruction execution time? One instruction execution time for non-pipeline and for pipeline. One instruction execution time for non-pipeline and for pipeline. So one instruction execution time will be, this is the ideal situation. So for the non-pipeline, you already know that is Tn. And for the pipeline, because we are considering the ideal situation, we are living in the ideal world. Okay, because you are living in the ideal world, one stage is taking Tn by k. One stage is taking Tn by k amount of time. So one instruction will take, I can say, Tn by k, and there are total k stages. So finally it also will be Tn. So both are basically taking same. This is the ideal world. Remember, as I told you, this is just the ideal world. We will come to the real world. Don't worry. Okay, we will come. So one instruction execution time is basically same in the ideal world, because in the ideal world we are assuming what we are assuming. Let me tell you, you have this non-pipeline CPU. Non-pipeline CPU, this I told you. So let me tell you again, whenever you have this non-pipeline CPU, okay, this is basically your single cycle execution. Okay, this is your single cycle execution of instruction. Okay, single cycle execution of instruction. So as I told you, you can easily see here. So in the ideally, I can say X instruction execution time, what that will like, or maybe you can assume what is the Y instruction execution time. What is the execution time of Y instructions? So this will take Y multiplied by Tn, right? This will take Y multiplied by Tn, because this is per instruction. This is per instruction. Okay, so this will take Y into Tn. What this pipeline will do? Can anyone tell me what this pipeline will do? For the first instruction, it will take k stages, right? For the first, it will take k stages. For the first, it will go through k stages. It will go through k stages. The remaining y minus 1 will go through only one stages, multiplied by one stage time, I can say, per stage time. So per stage time is what? That is Tn divided by k. So this is your pipeline time. Is this clear? Tell me, is this clear to everyone? See, very simple. I am saying that you have Y instructions. So the first instruction will go through all the k stages. Okay, but the remaining instructions, the remaining y minus 1 instructions, the remaining y minus 1 instructions, they will take only, they will go through only one stage. So total I can say y minus, I can say it will take k cycles. You can consider like this, k cycles, okay, for first instruction, for first instruction. So first instruction is taking k cycles, and these are for remaining instructions, remaining instructions. So the remaining instructions are taking this much amount of these many cycles, and this is the cycle time, and this is the cycle time. That's it. So this is your y instruction execution time. Now you tell me, if you have a lot of instructions, a lot of instructions, like finally I am asking you, if you have a lot of instructions, a lot of instructions, if you have, okay, a lot of instructions, if you have a lot of instructions. Now what will happen? Now what is going to happen if you have a lot of instructions? See, in this situation, when you have a lot of instruction, then just let's compare the speed up. Let's compare, let's find out the speed up. How much speed up we are getting when you have a lot of instructions? In case of lot of instructions, then how much speed up you are getting? Okay, or maybe sorry, before that, when you have a lot of instructions, then you tell me pipeline execution time. You tell me pipeline execution time. Tell me how much? What is the pipeline execution time when you have a lot of instructions? When you have a lot of instruction, then what will happen? You already know your formula. This is your formula, that if you have y, if you have y number of instructions, then this is time you are taking, tn divided by k. So if this y is very huge, if this y is very huge, then what is going to happen? Okay, no, so what I'm saying, sorry, so okay, okay, forget about this, because anyway, because if you have a lot of instruction, then it will take a lot of time. It's like, but let's compare the speed up. Let's compare the speed up when you have a lot of instruction. If you have a lot of instruction, then let's compare the speed up. What is the speed up? Speed up is basically how much time this non-pipeline was taking and how much time this pipeline is taking. So now you tell me, this non-pipeline is taking y into tn, and this pipeline is taking how much? This pipeline is taking k plus y minus 1, k plus y minus 1 multiplied by tn divided by k. Okay, so now you can notice, if this y is huge, if this y is huge, then what will happen? Because this y is huge, so what is going to happen? So this will cross this and this will cancel. So this tn will cancel with tn, so finally you will get k. Yes or no? So this is the ideally, so can I say this is the maximum speed up you can get? Tell me, because everything is ideal. See, so far the analysis that we have done, the performance analysis that we have done, we are doing a ideal analysis. Everything is ideal. Okay, like there is no, I can say, there is no disturbance. Everything is pure, I can say ideal scenario, the best scenario, the best case scenario. In the best case scenario, you are getting this speed up, and this is the number of stages, and this is the number of stages. So you tell me, now you tell me, so finally what you can say, what is the maximum speed up we can achieve? Tell me, what is the maximum speed up we can achieve? Tell me, we can achieve with pipeline. This is the maximum speed up, like this is the maximum speed up we can achieve with pipeline. With pipeline over non-pipeline, with pipeline over non-pipeline, what is that? That will be equal to number of stages in pipeline. Remember, this is ideal. As I told you, this is just the ideal answer. But nothing is ideal in the real world, right? Yes or no? But in the real world, nothing is ideal. This is the ideal answer. This answer is ideal. I can say this is the ideal situation. So this is the maximum speed up you can achieve. Maximum speed up you can achieve with pipeline over non-pipeline. And whenever you are finding speed up, always find for a large number of instructions. Okay. Whenever you are finding this, I can say, whenever you want to find speed up, this speed up you always have to find. Remember, this speed up by default you have to find for large number of instructions. Okay. Find for a large number of instructions. So for a large number of instructions, like if a large number of instructions are executing in pipeline and non-pipeline CPU, then you have to calculate the speed up. So you can notice that if everything is ideal, okay, then this is the maximum speed up you can achieve. And what is that? The maximum speed up that you can achieve. This is the maximum speed up, that is number of stages in the pipeline. This is the maximum speed up you can achieve. Okay. Now let's come back to the real world. Now in the real world, what will happen? Let's come back to that. In the real world, when you do this pipelining, in the real world, when you do this pipelining, that what will happen? Then the stages, their time might increase. It might be possible. It may be possible that, for example, here the washer is taking 1 hour. Let's see the real world. Okay, now let's consider the real world. In the real world, what will happen? Real-time analysis. So in the real-time analysis, what can happen? I can say real analysis. So the real analysis is like this. In the real analysis, when you convert this into pipeline, then it might be possible that for example, this washer, it was taking 3 hours, right? This was taking 3 hours for one instruction. Now it might be possible, for example, maybe this is taking 1.5 hour. Okay. It might be possible this dryer is taking maybe 1 hour. It might be possible this folding is taking maybe 2 hours. Okay. So you can see, and these are the entry stages buffers. Maybe these entry stages buffers also have some delay. Maybe they have some delay. Maybe this has delay 15 minutes. Okay, maybe this also has delay 15 minutes. Now you tell me a simple question I'm asking. In this real scenario, this is the real scenario that we are considering, the real analysis we are doing. In this real analysis, you tell me what should be the one cycle time. Because remember one thing, you should understand one thing, that all are synchronized by the same clock. Okay, all of them are synchronized by the same clock. All of them are synchronized by the same clock. All of them, they are synchronized by the same clock. So now you tell me, because they are synchronized by the same clock, so what should be? This is the clock. All these stages and all these entry stage buffers, they are synchronized by the same clock. So now you tell me, what should be the cycle clock cycle time? What should be the clock cycle time? So clock cycle time means, okay, please understand like this. Please understand like this. Clock cycle time means within this time, you one is like whatever stage you take, that should be able to complete its work, right? Yes or no? Yes or no? Cycle time should be such that the cycle time that you fix, because remember, all the stages, all the entry stage buffers, all they are synchronized by the same clock. They are synchronized with the same clock. They are synchronized. Okay. So whatever cycle time you give me, within that cycle time, every stage should be able to complete its work. Yes or no? Whatever cycle time you give me, in that cycle time, every stage should be able to complete its work. And remember, putting this information here is work of stage. Yes or no? Like, for example, if you want to put this information here, that is also this stage responsibility. Putting this information here, that is also this stage responsibility. So remember, putting the information in the buffer, that is also stage responsibility. So every stage should be able to complete its work. So you can notice this is taking a lot of time. So your cycle time should be like this. This is the maximum plus 15 minutes of delay. Okay. Assume that you have this here. Okay. Assume that you have this one here. If you have this, I can say interstage buffer here. If you do not have this interstage buffer, then there is no need, because see, if you do not have this interstage buffer, okay, but anyway, the point is very simple. Actually, you should, every stage should be able to complete its work. This is important. Okay. And putting this information here in this entry stage buffer, you are putting this information. That is also responsibility of this stage. That is also responsibility of this hardware. Okay. So basically, whatever your cycle time should be such that you are, every stage is completing its work. Okay. So this is, should be your cycle time. So like this is the real analysis. Okay. Now let's, so let me move on. Okay. Here actually what I want to tell you, here actually I want to tell you, when all the stages are balanced, like this is the ideal situation. In the ideal situation, you note the maximum. In the ideal, this is the ideal situation. Okay. In the ideal situation, your maximum speed up that you can achieve, that is the number of stages. Number of stages in the pipeline, that is the maximum speed up that you can achieve. Okay. In the real world, what will happen? In the real world, when you go to the real world, then in the real world, what will happen? This will happen. In the real world, I can say, in the pipeline, so you have this type of pipeline. Let's assume your pipeline is like this. Your pipeline has this stage, then you have entry stage buffer, then you have this stage, then you have entry stage buffer, then you have this stage, then you have entry stage buffer, and so on. Okay, and so on. Let's assume. Now, let me assume that this is taking some time. Maybe, okay, maybe this is taking 2 nanosecond. Maybe this is taking 4 nanosecond. Maybe this is taking 3 nanosecond. Maybe this is taking 1 nanosecond, 1 nanosecond, 1 nanosecond. Then in this situation, what should be your cycle time? Because all these are synchronized by the same clock. They are synchronized by the same clock. So for this clock, what should be the cycle time? What should be the cycle time? Remember, one stage, one per, I can say, one stage. Okay, it will do its one cycle. Okay, so it will do one cycle. It will do its work in one cycle. So what should be the cycle time? The cycle time, remember, whatever cycle time you fix, in that cycle time, all the stages should be able to complete the work. So the answer will be 4 nanosecond plus 1 nanosecond. Okay, this will be your answer. So your answer will be 5 nanosecond. This is the cycle time. Okay, because the reason is very simple, because all the stages and all the entry stage buffers, they are synchronized by the same clock. So whatever cycle time you are deciding, they, in that cycle time, all the stages must be able to complete their work. Okay, so for example, even this stage also should be able to complete the work. So the cycle time that I am deciding, that should be decided like this, so that every stage should be able to complete the work. So that is the reason answer is 4 nanosecond plus 1 nanosecond. This is your 5 nanosecond. Now you tell me, this is the gate question. So let's solve it. Let's solve this gate question. Tell me the answer for this one. This is gate 2004. Gate 2004 question. What is the answer? A 4-stage pipeline has the stage delay 150, 120, 160. So there is a 4-stage pipeline. You have a 4-stage pipeline. There are 4 stages, and these are the stage delays. These are the like how much time every stage is taking. For example, the first stage needs 150 nanosecond to complete its work. Okay, this stage needs 160 nanosecond to complete its work, and the last stage needs 140 nanosecond to complete its work. Okay, the registers that are used between the stages have delay of 5 nanosecond each. Okay, so every register having 5 nanosecond, every register that has 5 nanosecond. Assuming constant clocking rate, the total time taken for 100 data items in the pipeline will be. So very easily you can see that. First of all, you tell me what is the cycle time. First of all, what you tell me what should be the cycle time? How much should be my cycle time? How much should be my cycle time? Okay, remember this point. One thing you should understand, that cycle time means basically how much time I should give to per stage. Basically, it's like average per stage time, right? Yes or no? It's like basically per stage will be spending this much amount of time. Every stage is going to spend this much amount of time. So what should be my cycle time? That should be 160. That is the maximum. 160 plus 5 nanosecond. So that will be 165 nanosecond. Okay. This will be the cycle time. So what will happen? What will happen? This will happen that every stage will spend 165 nanosecond. Okay. Every stage, remember, every stage will spend 165 nanosecond. Whatever stage you take, that will wait for, or I can say that will spend 165 nanosecond. Okay. So this is the cycle time. You can very easily see. Now you tell me, for the 1000 instruction, how much time you will need? In the pipeline, this is a pipeline, no information is given, so you can consider ideal pipeline. No information is given to you in this question, no other information is given to you, so you can consider this as an ideal pipeline. So now you tell me, for 100 items, for 100, I can say, instructions, how much time you will need? For the first instruction you need, for the first instruction you have to go through all the stages, right? For the first instruction you need 4 cycles. For the first instruction, this is for first instruction, right? The first instruction should go through all the should go through all the stages. So for the first instruction you need 4 cycles plus, this is for first instruction. After this, after this, after this, you tell me, the remaining instructions, they need only one cycle. They remaining, okay, the remaining instructions, these remaining instructions, they only need one cycle. So finally, what will be my answer? Answer will be 5 plus 4, 9, 9. These many cycles I need. For 1000 instructions. So finally, the question is asking for time. The question is asking for time. So that will be 1111003 multiplied by 165 nanosecond. Tell me, what is this value? You can calculate. What is the answer for this one? Nanosecond. So you can, the question is asking in the microsecond. The answer is given in the microsecond. So what you can do, you can like 10310 this multiplied by, you can call it microsecond. You can convert this into microsecond divided by 1000. Okay, divide by 1000. So now you will get your answer in the microsecond. So now can you calculate this? 165, and almost it will be very close to 165. The answer will be very close to 165, right? Yes or no? The answer is going to be very close to 1, because they are almost same. They are almost same. You can notice these two are almost same. So the answer is going to be slightly more than 165, slightly. Okay, very slightly more than 165. So you don't have to calculate. Your answer will be this. There is no need to calculate. You can simply answer this. Now tell me the answer for this one. Look at this question. Tell me the answer. This is Illinois University question. Tell me the answer. Consider two different machines. There are two different machines. The first has a single cycle data path. Okay. Tell me. Do you remember this? I told you about this. Do you remember this? Do you remember this? I told you about this. What it means? I told you about this, right? Single cycle data path. Single cycle data path. That is your non-pipeline, right? Yes or no? So a single stage non-pipeline machine. So this point I told you, do you remember? I told you this point, that basically non-pipeline, when you do not have any pipeline, it simply means that you have a single cycle data path. Okay. Every instruction will execute in a single cycle. In a single cycle, you are doing all the things. Okay. You are doing all the things: instruction fetch, decode, execution, write back, data memory, access memory. So basically, as I told you, non-pipeline processor, that is same as single cycle data path. Is this clear? In the GATE exam, they can give you this. For example, in the GATE exam, they can give you that there is one machine, there is a machine which is using single cycle data path. Are you getting my point? Is this clear? So this single cycle data path, it simply means non-pipeline machine. Okay. Now you tell me, with a cycle time of 50 nanosecond, in 50 nanosecond, how many instructions are happening? Tell me. Tell me. In 15 nanosecond, how many instructions? One instruction is happening, right? Because this is a single cycle data path. Array, because this is single cycle data path means one instruction, one cycle. One instruction is happening in one cycle. Okay, in one cycle, one instruction is happening. So one instruction is happening in 15 nanosecond. Okay, the second is pipelined machine with 5 pipeline stages and cycle time 3 nanosecond. Now the question is asking for speed up of pipeline machine versus single machine. There are no stalls. No stalls means basically the question is talking about ideal situation. The question is talking about the ideal situation. Now you tell me, the question is talking about the ideal situation. In the ideal situation, what your answer will be? In the ideal situation, what your answer will be? No, see, okay. In the ideal situation, this answer will happen. Like in the ideal situation, see, this simple point I am telling you, note, when no stalls, okay. In this is basically ideal situation. You can consider this is an ideal situation. Okay. Anyway, you can just calculate. Okay, just forget about it. You can just calculate. See, you can just simply calculate the question. You don't have to by heart anything. You can just calculate. Okay, here, tell me the pipe. How much time pipeline machine will take for n instructions? If you have n instructions, how much time for n instruction? How much time non-pipeline will take? How much time non-pipeline will take? That will take n into 15 nanosecond, right? And how much time pipeline will take? Because this is given to you that this is a single cycle data path, means non-pipeline machine. The cycle time is 15 nanosecond. 15 nanosecond means one instruction is happening in 15 nanosecond. Okay, one instruction happening. So an instruction will happen in this much amount of time. In the pipeline, what will happen? In the pipeline, 3 nanosecond time is given to you. The cycle time is given to you. And there are 5 stages. So you can notice the first instruction will go through all the 5 stages, correct? The first instruction, this is for first instruction, 5 stages, or I can say 5 cycles. The first instruction will go through all the 5 stages. So the first instruction needs 5 cycles plus the remaining instructions. These are the remaining instructions. They need only 1 cycle. These are the remaining instructions. And these remaining instructions, they only need 1 cycle. They only need 1 cycle. Okay, so these many cycles multiplied by cycle time, which is 3 nanosecond. So what is the speed up? So what is the speed up? Speed up simply means that how much speed up you are getting. Speed up. So that will be basically non-pipeline execution time. How much time you are having for non-pipeline divided by pipeline execution time. So your speed up will be what? Your speed up is non-pipeline execution time is for any instruction you are taking 15 nanosecond, this much amount of time divided by pipeline execution time. Pipeline execution time is you are taking 5 plus n minus 1 multiplied by 3 nanoseconds. Now, when you are calculating the speed up, assume that n is very large. Okay, when you are calculating for large number of instructions, okay, for large number of instructions, so you can assume that this n is huge, this n is very large. If this n is very large, then what will happen? Because this n is very large, so this will cancel out. So your final answer will be 5. So your speed up will be 5. So this is your final answer. So for this question, the answer is 5. Okay, very simple, right? Yes or no? Is this clear? Is this clear to everyone? Let me know. Now let's move on. So tell me the answer for this one. See, this another question. This another question. You have another machine which has 4 stages. So this machine has 5 stages. This pipeline has 5 stages. Okay. And cycle time is 3 nanosecond. And this pipeline has 4 stages and cycle time is 3.1. Assume no stalls. No stalls means again ideal situation. It's like, okay, ideal situation. Now you tell me which is faster, which you will prefer. So the question is very simple. The question is saying that there are 2 machines. One is pipeline machine 1, another machine 2. There are 2 machines. This machine has 5 stages but 3 nanosecond is the cycle time. And this machine has 4 stages. Number of stages are less, but the cycle time is just 3.1. This is the cycle time. You tell me which you will prefer. Which will you prefer? Tell me. Which will you prefer? See, for one instruction which you will prefer, for one instruction, which you will prefer for one instruction only. Like if you have only one instruction, for one instruction, which will you prefer? For one instruction, this PL1, this PL1 will take 15 nanoseconds, right? Okay, it will take 15 nanoseconds. And PL2 will take almost, I can say 12.4 nanosecond. So for one instruction, this is definitely better. For one instruction, you can see that for one instruction, this is better. But this is for one instruction. Now you tell me, in the real life, do we execute only one instruction? So should I prefer PL2? Should I prefer PL2? Is there any reason to prefer PL2? Should I prefer PL2? No, 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 no. Because in the real life, we execute many instructions. So if you are executing many instructions, okay, a lot of instructions if you are executing. So when you are executing a lot of instructions, then ultimately, it is executing one instruction in one cycle, right? Yes or no? When you have a lot of instructions, just consider like this, a lot of instructions you have. So when you have a lot of instructions, then ultimately what will happen? Ultimately, this will happen that in this PL1, okay, because you have a lot of instructions, so you can just assume that in every cycle, one instruction is coming, right? Yes or no? Correct or not? The initial, like, because you have a lot of instructions, so forget about the initial feeling. Forget about the first instruction. Because you have a lot, you have a large number of instruction. So when you have large number of instruction, forget about the first instruction. So ultimately what is happening in this pipeline, in one cycle, one instruction is coming. One cycle, one instruction, one cycle, one instruction, one cycle, one instruction. So I can say that in this PL1, in one cycle, one instruction, one cycle, one instruction. So 3 nanosecond per instruction you are taking basically. And in the PL2, what you are doing? PL2 also, one instruction, one cycle, one instruction, one cycle. Okay, in every cycle, one instruction is coming, but you are taking 3.1 nanosecond per instruction. So which is better? So ultimately, this is better, right? So you can see that when you have a lot of instruction, then this PL1 is better. So ultimately, you should prefer this PL1. This is preferred. You should prefer this PL1. Okay, let's move on. This is a GRE question. This is a GRE computer science question. Can you tell me the answer for this one? This is a GRE computer science question. This is a very nice question. Can you tell me the answer? GRE computer science. Can you tell me the answer for this? Two processor, M5, M7. There are two processor, same instruction set. M5 has 5-stage pipeline. Okay, this has 5-stage pipeline. Cycle time of 10 nanosecond. There is cycle time of 10 nanosecond. M7 has 7-stage pipeline. Cycle time of 7.5 nanosecond. Which of the following is or are true? Tell me the answer. Which of them is or are true? Which of them is true? First, let's see the option 2. The latency of a single instruction. The latency means basically how much time you are taking for a single instruction. How much time you are taking for a single instruction that is shorter on M7 than M5. Is it true? Is this true? For one instruction, what will happen on M5 and 7? See, the two pipeline are given to you. One is M5 machine, another is M7. In this, you have 5 stages. There are 5 stages. And the cycle time is already given to you, that is 10 nanosecond. This 10 nanosecond is the cycle time. And here you have 7 stages. There are 7 stages. and 7.5 is the cycle time. 7.5 nanosecond, that is the cycle time. So now you tell me a simple question I'm asking. For one instruction, what will happen? One instruction latency. Tell me what will happen for one instruction. So for one instruction, M5, this pipeline will take how much time? Okay, for one instruction, you have to go through all the stages. You have to go through all the stages. So that will be like 50 nanoseconds. Okay, for one instruction, you have to go through all the stages. You have to go through all the stages. And every stage is taking 7.5 nanoseconds. So that is, you can see that is greater than 50, right? That is greater than 50 nanosecond. So for one instruction, which is better? For one instruction, which is better? For one instruction, this is better. This M5 is better for one instruction. Okay, so finally I can say is shorter. So this statement is false. Okay, what about the next statement? This statement, M7 pipeline has better maximum throughput than M5 pipeline. This M7 pipeline throughput. So you calculate the throughput. Let me tell you what is throughput. What is a throughput? This word you have seen many times in your computer network operating system. What is throughput? What is this concept of throughput? Throughput always means that how many things you can do per unit of time. Okay, number of things done, number of work done per unit of time. Per unit of time. Whatever field you take, computer network operating system, whatever you take, then this throughput, this simply means that how much work you have done per unit of time. So here I can say this throughput will be number of instructions you have executed per number of instructions executed per unit of time. Per unit of time, right? In 1 unit of time, how many instructions you are executing? Now you tell me, okay, in this M5, for an instruction, how much time you are taking? For an instructions, how much you are taking for an instructions? How much time you are taking? Tell me. For an instructions. For n instructions, what is the time you are taking? You are taking 5 plus n minus 1 multiplied by 10. And how much time you are taking here? You are taking 7 plus n minus 1 multiplied by 7.5. These many nanoseconds here, these many nanoseconds here. Okay, so you tell me what is the throughput here? What is the throughput here? Throughput means per unit of time, how many instructions you are doing per unit of time in 1 nanosecond. Like in 1 nanosecond, how many instructions you are doing? In 1 nanosecond, these many instructions we are doing, right? Yes or no? In 1 nanosecond, these many instructions we are doing. In 1 nanosecond, these many instructions. And what is the throughput here? What is the throughput here? In 1 nanosecond, how much time, how much work I am doing, how many instructions I am executing? Okay, now you tell me which has better throughput. When you have like if your number of instructions is more, if you consider number of instructions is more, then which has better throughput? If you consider number of instructions more, like this M5 throughput, and this M7 throughput. Okay, so this M5 throughput is like n instructions you are doing in this much amount of time. In this much amount of time. Here n instructions you are doing in this much amount of time. Okay, so if you have large number of instructions, if you calculate for large number of instructions, okay, always like calculate for large number of instructions. So if you are calculating for large number of instructions, then this will cancel out, this will cancel out. So here you will get 1 by 10 and here you will get 1.75. So you can see that this has better throughput. Yes or no? This has better throughput. This M7 has better throughput. M7 pipeline has better throughput, has better maximum throughput. See, the question is asking for maximum throughput. It simply means when the question is asking here for maximum throughput, it simply means it is asking for large number of instructions, right? Yes or no? Because the question is asking for what is the better maximum throughput, am7, am5. They are giving like which will give you better maximum throughput. So when the question is asking for maximum throughput, it simply means that the question is asking for large number of instructions. Like you are executing a large number of instructions, then definitely this am7 is better. Programs executing on am7 will always run faster than program executing on am5. Is this true? Is this true? This is false. Why? For example, if your program has only one or two instruction, right? Yes or no? If your program has only one instruction, let me assume your program is very small, only one instruction program. Your program is one instruction program. Then of course this always is false, right? This always, because of this always, this statement is false. So finally answer will be option A. This option is the answer. So in this question we have done what is throughput. We have covered the concept of throughput. We have seen the latency of one instruction. For one instruction, how much time you are taking. Okay. We have seen the concept of throughput, how to calculate the throughput. Throughput concept is very simple. This is basically the amount of work done per unit of time. How much work you have done per unit of time. Like for example, how many instructions you have executed per unit of time. So you can calculate throughput of M5, throughput of M7. This is the throughput of M5. You can see this is the throughput of M5. This is the throughput of M7. You can calculate, and then you can see which is better for large number of instructions, which is better. So definitely M7 is better for large number of instructions. Okay. So very simple. This is your question. So, okay. I think this is enough for today. Actually, my voice is also, my throat. See, for the last 7 days, I have had some throat infection. So because of that, I could not take classes. Okay. So right now also my voice is not very good. Uh, so, okay. So I think this is enough, and we will continue in the next lecture. So tomorrow night, okay, tomorrow night we will continue this pipeline. I will cover. See what I will do. Each and every question, each and every gate question, I will not leave any gate question. See, for the cache memory, Sachin has already covered all the gate questions, right? For the cache memory, I think Sachin was telling me that all the gate questions he has covered, complicated questions and easy questions, all the questions he has covered. So similarly for the pipeline, each and every gate question we will cover along with some standard questions. Like for example, so far what we have seen, 2-3 gate questions we have seen, and 2-3 standard questions we have seen, correct? Okay. So remember one thing, that tomorrow we will continue this pipeline session. We will continue, and I promise you each and every gate question we will cover along with the standard questions. Okay, all the standard questions that are there in the standard resources. Okay, whatever question they can create in the next gate exam, in the gate 2023, whatever question they can create. Okay, all the variations, all the questions, all the gate questions, everything I will cover. Okay, so don't worry about the pipeline. Okay, in this lecture, like, okay, forget about tomorrow, forget about yesterday. Okay, today you tell me in this lecture, whatever I told you, did you understand, and do you have any doubt? I will answer all your doubt. Please tell me, please let me know, did you understand everything, or do you have any doubt? Just only focus on this lecture. Don't worry about tomorrow and yesterday. Okay, only focus on today. Okay, so tomorrow what we are going to do, we will continue this pipeline session at night. Okay, and in the morning you have this all India mock test 2. Okay, go classes all India mock test 2. One thing I want to tell you, that a lot of effort we put whenever we are creating mock test. Okay, you can see the quality of mock test. You will not very like sometimes it will happen because we are also human being. Okay, so mistakes can happen. It's not like a perfect paper we will create. Okay, some mistakes can happen, but we rectify them. For example, if there is some question and some mistake is there, then you can tag us in the comment. In the comment you can say that, sir, in this question this is the mistake, we will correct it. Okay, so this is the best facility on the Gate Overflow. I can say in the Go classes, this is the best facility in the Go classes test series, in the Gate Overflow test series, that whenever you have some doubt in the question, in the answer, if you have any doubt, then what you can do, you can just comment, you can let us know. Okay, and we will answer, we will resolve your doubts. Okay, if there is any, I can say, typing mistake in the question, we will correct it. Okay, so what I'm saying, in each mock test we are putting the best quality questions. Like there each mock test, let me tell you how much time we are taking. So Sachin and I, we don't live together. Like we live 20 kilometer apart. We live in Jaipur, in the Jaipur city we live. Okay, now right now I am in my own house, as I told you. Like last November, in the last year, in the November month, I purchased my own house in the Jaipur city. So now I and Sachin, we are 20 kilometer apart. But still, for each mock test, remember, for each mock test, we sit together for 2 3 days. Okay, for 2 3 days we sit together, we discuss. We want to give you basically the real feel of Gate exam. See, I don't want to say this, but anyway, what I see, this is just honestly, I'm saying that in most of the test series in the market, there are many test series. Some are good. I'm not saying that all are bad, but in most of the test series, what happens, they put the Gate questions replica. The Gate previous year questions, they will put the replica of those questions. Okay, so when you are already familiar, when you attempt those mock tests, then you are already familiar with those questions. You already know you already know how to approach those questions, so you will get more marks. Okay, naturally you will get more marks, right? Yes or no? Okay, you will not feel any difficulty, you will just get more marks. But in the Go classes test series, think about it. In the Gate 2023, they will not ask you those questions which they have already asked. Some questions will be there, of course. Okay, in some questions, but there will be many new questions. Correct? Out of 65, there will be 65 questions. Out of 65 questions, or more than 30 questions will be brand new, right? Yes or no? New questions where you have to think how to solve it, where you have to think about the approach. So more than 30 questions will be brand new questions. So this experience we want to give you in our mock test. Okay, in all the mock test we are putting some brand new questions which you can think. Okay, so for every mock test we are putting a lot of efforts, let me tell you. Okay, a lot of effort goes behind every mock test, and behind all India mock test, more effort has gone. Okay, so for every mock test, if we are giving 3 days, then for all India mock test we are giving almost 5 days. Okay, so the tomorrow will be all India mock test 2. Okay, second all India mock test will be tomorrow. And attempt that mock test, don't worry about the marks, attempt it. Okay, do not leave it, do not skip it. Okay, do not keep it pending. Don't worry about, we have a lot of mock test. Okay, we have total 15 mock test in the Gate Overflow and Go classes test series. 15 is a lot of number. Okay, so you don't have any shortage of mock test, you have 15 quality mock test. So that is the reason I'm telling you, tomorrow attempt the mock test, all India mock test 2. You should attempt it, do not leave it for later time. Okay, so sleep now at this. Okay, now we will terminate this session. Okay, sleep immediately, you sleep, go to sleep. Okay, tomorrow wake up with a fresh mind, you wake up and and give the mock test. Give the mock test like you are giving the Gate exam. Tomorrow you will definitely enjoy a lot. Okay, the mock test is, I can say, it is just a true reflection of the Gate exam. Okay, it is a true reflection of Gate 2023 exam. Just like all India mock test 1, this all India mock test 2, this is also going to be very nice. Okay, one more thing I want to tell you, that all India mock test 1 was little bit harder. Okay, it was little bit harder. Okay, but all India mock test 2, tomorrow the mock test will be more balanced. Okay, so tomorrow you will enjoy the mock test more than you enjoyed all India mock test 1. Okay, so if you already enjoyed all India mock test 1, then tomorrow you will enjoy much more. Okay, so thank you everyone. See you tomorrow, and we will finish this pipeline. Each and every gate question we will finish. Do not worry about it. Okay. Okay. Thank you everyone. See you tomorrow.